做的都平面，然后这个工很多，然后拿着书挡在这儿，拿起光照，照是这个书拿走，再一洗，用空气好像不用。看不懂是画一个问题，待会儿带学生自己去这个修课，他是专门抓紧去玩。求到这个练习，我是。因为他一球到嘛，是绝对在就是如果他大的话，那就是这么小一个。就相当于两项，一个2个8，先放到这个，不是，晚上的每天带，或者是水课，因为晚上。就是最平安的时候，我确实。但是我觉得这个可是的事情，也是说到别生，那我是那个时间去。
Everybody's moving to the back. But there's homework out on termite. I'll shift it to Canvas. Use Firefox or Chrome. Chrome's better. Look. Homework, homework, homework. 10. Homework 10 is due November 26th. Is that 1 week?
Yeah.
Today's 19, 9 and 7.
Yeah.
It's 1 week. But we don't meet Wednesday. Right.
So we have Thanksgiving holidays, so can
What are you saying?
Thanksgiving Day, so we have some other days to
You don't want homework.
if you like.
Okay, you can do it tonight. Do 2 homeworks tonight. I think we started talking about last time that that circuit, right where we had a current source, and we had capacitor and a resistor in parallel, and we had an input X of t, and we're looking for the voltage Y of t. So we have GY is the current going through the resistor plus current going through the capacitor is C dy dt, and that's equal to input current. And so we take the Fourier transform, we get something like H of omega times y bar of omega Fourier transform. That's equal to the Fourier transform of the input. And so that should be 1 over H of omega. So H of omega equals 1 over G plus J omega times C, which is J, which is 1 over J times C, capacitance 1 over omega minus J omega O, and omega O is C divided by G. No, it's G divided by C, right? Factor out J, C, minus J. So that would be minus J, G over C. How many of you have ever worried about integration in the complex plane? You ever thought about that? Integration. In a complex plane. Who has done that? No. Have you ever heard of Cauchy's theorem? You have? Can you tell me what it is? Anybody? Well, it's something like this. If you have a contour C in the complex Z plane, and I integrate around this path, see, it turns out that at some point inside z0, point z0, the f of z, I'm going to use script here, f of z0 is equal to integral over a contour of f of z divided by z minus z0 times dz. Have you ever seen that? You have? Nada, nada, puh, puh, no puh. Let me give you an example. Oh, just looking at this formula here, it's amazing that you can find f at z0 by integrating this around that contour, which means you need to know f at every point on the contour. If you know f on every point on the contour, this says you integrate that divided by z0, it gives you the function at z0. Let's give an example. Let's say there's z0, and I'm going to put a circle around z0. I'm going to let f of z equals 1. So what does that mean? It means the following, that f of z is 1, f of z0 is 1. So that says 1 equals 2. The integral around this circle, contour C. And I'm going to write z equals to z0 plus r ej theta. So here's z0, point to 0, and then a point on the circle, and that circle has a radius of r. And so dz is equal, that's a constant, r j theta e to the j theta. And so we're going to integrate theta from 0 to 2 pi. F of z is 1. Z minus z0 is r ej theta. And dz is r, no theta there, rj e to the j theta times d theta. And you see r ej theta goes out. Oh, does this come out what? This is 0 to 2 pi j ej theta d theta. So this comes out to 2 pi j. So you know what I need to do is modify 1 over 2 pi j. Okay, so here we are, Cauchy's theorem. Here's Cauchy's integral theorem. He's not doing it. Let's see what the people at Mathematica say. Get rid of that place. Got another one. Ah. I'm just looking for the answer. We'll have to take what I have to be the gospel. Two pi j. Looks like that's it. So what's interesting here is that this says that this function here has a simple pole at that point. Now, if this thing has two poles, two simple poles, then the integral around the contour at pole 1, and I got another pole Z2. Then you know what you can do is at f of z over z minus z1, z minus z2 dz, that's equal 1 over 2 pi j, so I'm going to just say 2 pi j times f of z1 divided by z1 minus z2 plus f of z2 divided by z2 minus z1. And so this is 2 pi j times 1 divided by z1 minus z2 times f of z1 minus f of z2. So that's that. So we know integration in the complex plane. So we have back here, we can calculate the transfer function x of omega equals 1 is h of omega, y. H of omega times x of omega. And we have h of y is 1 over j times c times omega minus j omega 0 times x of omega. Okay? Now, suppose omega, x of omega is, let's say x of t, random function x of t, has a autocorrelation function Rxx of omega Rxx of tau, is equal to delta of tau. So we know Wiener-Kenshin. Wiener-Kenshin, don't forget Big L. It says, Big Al says that the Fourier transform of the autocorrelation function of the autocorrelation Rxx of tau is the power spectral density. So this stated as the power spectral density of the random variable x as a function of frequency is the integral from minus infinity plus infinity of Rx x of tau e to the minus j omega tau d tau. And that the autocorrelation function of tau is 1 over 2 pi Sx of omega e to the j omega tau. Now integrate on omega. Power spectral density. So this says then that y squared of omega is h omega squared times e. Let's say sy of omega is equal to Sx of omega. By the way, how do you get power spectral density of a time signal? Well, this is Wiener, or this is a linear system result, because the power spectral density of the output is the transfer function squared times the input. And so you have the autocorrelation function of x. You can calculate its power spectral density. Let's say x of t has Rxx of tau is delta tau. Actually, it's the absolute value of tau. And so if I want to calculate the spectral density of x, I got to take the Fourier transform of not x, but its autocorrelation function. And that is minus infinity to plus infinity delta tau e to the j minus j omega tau d tau. What's that equal to? 1, 1, 1. 1, 1. This thing is always a symmetric function. So you could integrate from 0 to infinity. Multiply by 2. remember the Gaussian function delta sigma of tau looks like that. But this is an even function. Take the absolute value. So the input transform looks like that. Looks like it's 1. And so we have the output's power spectral density. It's what? Del Sy of omega is h of omega squared times 1. H of omega is 1 over j times c. 1 divided by omega minus j omega 0, and omega 0 is g. It is g divided by c. G divided by C. I take h of omega squared is 1 over c squared What would you say is the answer? Well, I got 1 over c squared. We got to take absolute value. Would you say it is omega squared? Plus omega 0 squared? Is that what you would say? So this is the transfer function. Now I'm going to calculate y. Sy of omega is 1 over c squared omega squared plus omega 0 squared. Can we calculate the autocorrelation for y? We can. Ry of tau is 1 over c squared. Don't forget the 2 pi. Don't forget the 2 pi, because 1 over 2 pi times the integral from minus infinity to plus infinity, e to the j omega tau d tau. Divide that by omega squared plus omega 0 squared. Is everything okay now? Can we evaluate that integral? Well, let's see if we can bring Cauchy's theorem into play. Omega squared plus omega 0 squared is omega minus j. Omega 0 times omega plus j omega 0. Right, we got two poles. Two poles now. One at j omega, the other at minus j omega. So let's write RYY of tau is 1 over 2 pi c squared. Now we're going to do the integration from minus infinity e to the j omega tau d omega omega minus j omega omega plus j omega. We have two poles, right? We're working with two poles. Okay, but what's the contour? This integral is along the omega axis. And so I'm going to draw a picture here of the omega plane. It's complex, but we're really integrating along this line in the omega plane. And we found out there's a pole here and a pole there. There's one at j omega, there's a pole at minus j omega 0. Got two poles. Now, where's the contour? We're lacking a contour. Well, I'm going to close this thing a semicircle. I'm going to make the radius of that semicircle r. And so now, here's the contour. We integrate here, and then we integrate here, down here, and we're back to the point. So we have a close contour. Got one pole inside that contour. But would it be okay if I integrated this way, or integrated down this way and then across? Right? I got my choice here because I'm really interested in the integral from here to here, minus infinity. I'll say this is minus r to plus r. And so we write this minus r to plus r. We don't have infinity. R's going to get bigger and bigger and bigger and bigger. But now, what about integration up here? Well, let's just check. Let's say omega is equal to, at this point here, it's j times r. Right? It is j times r. R's going to get real big. Well, if we're integrating j times r, omega is going to be J times R, and we're going to be integrating. Theta is R EJ theta. Right. So here's theta. We're going to be integrating, but it looks like omega is R cosine of theta plus R J sine of theta. So now I'm going to put these two in the exponent. E to the j omega tau is j tau R cosine theta plus j R times sine of theta. And so we have e to the j tau R cosine of theta minus, minus tau R sine theta. Now, sine theta is always greater than 0 on sine theta is greater than 0 on that curve. And as r goes to infinity, what happens to the integrand? Goes to 0. And so e to the j omega tau goes to 0 on semicircle. So we'd be okay. Look, if we chose the contour down below, theta would vary from pi to 2 pi, and sine theta would be negative, so it would blow up if tau is positive. So here's the conclusion. Conclusion. Take upper contour if tau's positive. Conclusion. Take lower contour if tau's less than 0. That's the bottom line. So f of omega is equal e to the j omega tau for the upper contour integration. Upper, this will be omega minus or plus j omega 0. Right. So this is the function. So we have the answer. There's a pole at omega equals to j omega 0. Sy R, Y, Y of tau equals to. You know what, I should probably put the 2 pi c squared in there. Two pi c squared. It's in that function. So RYY is equal to RYY is this integral from here to here. This integral is 0, so it's evaluated only at that pole j omega. So RYY is e to the j tau times what? J omega 0. Divided by 2 pi c squared j omega 0 plus j omega 0. Oh, I forgot the 2 pi j, right? 2 pi j. Cauchy's theorem. I take this 2 pi j over here. 2 pi j. 2 pi j. Look at that. 2 pi goes out, and the j goes out. We have RYY. Isn't that simple? RYY of tau equals to e to the minus omega 0 times tau divided by c squared 2 omega 0 c squared. There's your answer. Oh, that's for tau greater than 0, isn't it? What would we do if tau is less than 0? Tau less than 0. By the way, this integrate here like that. Tau less than 0, we want to integrate like that. Now, Cauchy's theorem means that you integrate in this direction. So that means the integral from this point to that point, in this case, in this contour, integral from minus r to plus r is equal to minus 2 pi j times f at minus j omega 0. So you'd have to, the reason I put a minus sign, because the Cauchy's theorem integrates clockwise, but our integral is here. And so the integral from minus r to plus r has to be reversed. We take the integration in the negative direction. Always at contour integration, you're always going clockwise. Clockwise. Right-hand rule, clockwise. So that means you got the minus sign. Okay, so So we can write RYY of tau equals to, you got a pole at omega equals minus j omega 0. So we have to fill in the function of 2 pi j minus 2 pi j minus 2 pi RYY of tau is minus 2 pi j. We have to put minus j omega 0. That would be e to the j tau minus j omega 0. And the denominator would be we have that pole located at omega plus omega 0. Take lower pole. Take lower pole. You would come up with, here's the answer, e to the plus omega 0 tau for 2 omega 0 c squared. And this is for tau less than 0. So what is the bottom line? You only have to worry about the simple poles in the plane. Is that complicated? Yes or no? Okay, you know how you can find the answer? You'd have to get a table of Fourier transforms. If you know the transform, you have to find the inverse transform. So what we've been doing is calculating the inverse transform. By the way, there's an old book by Papolis, and it's called the Fourier integral and its applications. Papolis. The Fourier integral. He doesn't call it transform. Fourier integral and applications. It's that book is a pretty old book, but I suppose he wrote it because it's important in random processes. X of t h of omega, x of omega, y of omega. The output y of omega is h of omega times x bar of omega. If I take the absolute value of both sides, like that, I get the power spectral density of Y. That's a transform of the time variable. H of omega squared times omega squared. Right. And this is Sx of omega. Example, a white noise N0 over 2. White noise. So the spectrum of white noise looks like this as a function of omega. And we'll call this the input power spectral density as a function of omega. It's just a constant. XF of omega equals to N0 over 2, noise. Shot noise could be resistor, noise from a resistor. If you take an antenna, point it to the sun, you get a lot of noise. So don't point your antenna to the sun. So white noise has every frequency. And what is its autocorrelation function? Rx of tau equals 1 over 2 pi integral from minus infinity plus infinity N0 over 2 e to the j omega tau d omega. This is N0 over 2 times delta of tau. White noise, the autocorrelation function of white noise is the impulse. So if we say Sy of F, the output from this system is N0 over 2. We need H of omega squared. So let's take this circuit here. This is X, and this is Y of t. We have, this is a voltage source. So the transform Y of omega is, it's a X of t transform. What is the transfer function of this? Okay, it'd be the current flowing, right? It'd be 1 over j omega c. That's the resistance of the capacitor over the sum It's a divider circuit. R plus 1 over j omega c. And that's 1 divided by 1 plus j omega r times c. And so we can write this as times x, that's an f, x bar of f. And so S, the output power spectral density of Y happens to be this thing squared. So it's 1 plus omega squared r squared c squared times the input power spectral density of omega. And the input power spectral density is N0 over 2. And how do we calculate the transform? Ry of tau is equal to N0 divided by 4. So this is filtered white noise. Right? Filtered. The power spectral density is always positive. Density is positive. And real. It's positive and real. That implies that Rx of tau is equal to Rx of minus tau. Symmetry. I'm going to give an example. X of t is a cosine omega 0 times t. Omega 0 is just a specific frequency. Omega 0 times t plus theta, where theta uniform, f theta 1 over 2 pi on minus pi to plus pi. X of t plus tau is a cosine omega 0 t plus omega 0 tau plus theta. And x of t plus tau it's going to be a squared this cosine function times this cosine functions, right? Sum and difference. Cosine sum and cosine difference. Right? Cosine A, cosine B is what? 1/2 cosine A minus B minus A plus B. Is that right? Yes. So that means you got 1/2, you got A squared over 2. Let's take the difference between this and this. Oh, that's tau, excuse me. T plus tau. Let's take the difference between that means everything subtracts out. Omega tau. Omega 0 times tau. No theta. Minus, we got to add these two. Cosine 2 omega 0 t plus omega 0 tau plus 2 theta. Now, I'm going to take the expected value with respect to theta, and it's going to be 0. The expected value of x of t plus tau, is a squared over 2 cosine omega 0 tau. Symmetric. So it looks like this. So this is cosine omega 0 times tau. The power spectral density, S of omega, is equal to, no, this came out to be A squared over 2. So A squared over 2 times the integral from minus infinity to plus infinity. I'm going to write cosine of omega tau, e to the j omega 0 tau plus e to the minus j omega 0 tau divided by 2 e to the j omega tau d omega. Oh, excuse me, d tau. So this looks like A squared over 4 delta omega minus omega 0, right? Delta omega plus omega 0. Symmetric. And so here's the power spectral density, omega. This is omega 0, and you have a spike at minus omega 0. 2 spikes. That's the power spectral density. Power spectral density of white noise, telegraph signal, exponential. And so forth. By the way, if you're building a radar system, I'm gonna put an antenna here. This sends out, and I have another antenna that receives information. Let's say I put out a signal. X of t. And I have a spacecraft here. I have a blob in space. This thing goes out and hits that blob, and it reflects. It reflects off of that blob, and it comes back into my receiving antenna. What can I do with this signal that I receive now? By the way, what X of t goes out and hits that target, what's going to come back? Is it going to be some amplitude times X of t? Plus noise. I'll call it N of t. Right, this signal has to go through all sorts of reflections, hits that spacecraft, and it comes back. What would we do? Suppose you send out a sine wave, X of t, and it hits the spacecraft and comes back. You just have a sine wave. That is, unless it's moving real fast. Then you would have a frequency shift. If the spacecraft is moving away, it would shift to the red, low frequencies. If it was coming toward, you would see higher frequencies. So I'm sitting here at this receiver and I'm receiving a signal like that. What's the best way to find out where this target is? Well, I just send out a bang, goes boom, boom. So I send out a bang, X of t, and I see coming back noise there. See this noise here? So I send out X of t, and I receive Y of t. I think if I did an autocorrelation, I might have some information. So probably what I want to do is cross correlation. And I want tau to be the delay time. So I have a computer here at the receiver, and it's got data of what was sent out, function of time, right? So I take that data as a function of time, and I'm receiving something, a function of time, and I do a correlation between the two. computer has to be pretty fast, right, to keep track of that. And, and so what happens here, coming out of the computer, the thing peaks up at tau. How long it took to send it, how long to come back. And so now, maybe if I just send a pulse like this, I can tell something about where it's located. Don't know much about how fast it's moving. But if I send out this signal here, I have a cosine output, but I have a cosine input plus some phase angle due to autocorrelation on that. And the phase angle would tell me something about the difference in frequencies. So I would know how fast it's going. But let me tell you what is the best signal, not today, but next time. So we're 2 minutes over. I owe you 2 minutes. Okay. Happy holiday. Turkey Day.